Hey, good morning, sir.
Good morning. Did you manage to finish the assignment yesterday, Keshav?
No, sir. I missed some part of it,
Okay.
and yeah, I got that file which you shared, but I haven't gone through. Like, I have not done that. I'll do it now today because I missed some earlier part.
Okay.
So I need to I was not able to complete that thing. Actually, my laptop is giving some problem. It's getting
Okay.
shut down in between. So mm, I need to show to the shopkeeper for the results.
Good morning, everyone. Danal, Tejas.
Good morning, sir.
So, did you manage to finish the linear regression yesterday? Is my screen visible to everyone? Okay, so today we are going to start our second topic, which is logistic regression. So any questions on the linear regression that we did yesterday? Were you all able to finish? Please speak up, please respond. Hello? Am I audible to everyone? Okay. This is tough when I don't hear any responses anyway. Okay, so logistic regression is the second technique that we're going to see in the regression chapters. So in the linear regression that we saw, so we had a set of features and we had a y variable which was continuous in nature. And we had a set of features which most of the time are numeric, which can be either discrete or continuous. And that is going to predict the y variable. And we also have the numeric features plus the categorical features. And that is going to predict the y variable. So in a logistic regression, we have something similar. We have a set of features and we have a y variable. But this y variable is going to have something called as a class, or we can say a category. So category means that a given record can be predicted as either this or this. That is class yes or a class no. So this is called as a category. Now in a categorical or a classification, this is also known as a classification method. You are classifying a certain record as either this or that. Now, in a classification method, there are three types of classification. One is called as a binary classification. Then we have a multi-class classification. And then we have an advanced technique called as multi-label classification. Now, let us not discuss about multi-label. So, this is a very advanced technique. So, let us leave it for the time being. So, let's focus on the two classes, binary class and multi-class. Now, a binary classification is a type of classification where the outcome has only two categories, yes or a no, or it could be 0 or 1, or it could be true or false. Okay, any one of these two. Okay, this is called binary classification. So if you look at real life examples of binary classification, so we have whether a person will get a loan, yes or a no, whether you will get a college admission, yes or a no. Okay, or whether this approach is acceptable or not acceptable, true or false. So we can say a certain, let's say, technique. So true or false. So wherever you have only two classes, this is called as binary classification. Then we have the second variety, which is called multi-class classification, where the Y variable can belong to any one of multi-classes where the classes are greater than or equals 3. Okay, for example, if I have to find out, given a certain, let's say, a book. Okay, so this belongs to which category, whether it is a thriller or whether this is a romantic book or whether this is a science fiction or whether it is, let's say, a biography or whether this is non-fiction or a fiction. Okay. So what are the characteristics that define a certain book as thriller or this any one? So here we have 6 classes and a certain book can belong to any one of these 6. So this or this or this. So this is called as a multi-class classification. So logistic regression deals with mainly a binary classification, even though it can be used for multi-class also, but mainly it is used for a binary classification. Any questions in this? Is the introduction part clear to everyone?
Yes.
Okay. Now let us talk about the data types. So data in a logistic regression. The data in a logistic regression can be a combination of either a number or it can be a category or it can be a combination of both numbers and categories. Whereas the Y variable is always a category. So it can either be value 0, 1, or it can be yes, no, or whatever it is. So in Python, whenever you have a category which is not described in terms of numbers, for example, 0, 1, so you have to convert them into numbers. So Y and N is converted into 1 and 0, 0 and 1, whatever may be the case. And if it is true or false, it has to be converted into the numbers before you can build the model. Okay. So the data can contain any of these combinations. Now let us see a little bit of the maths part, that how is logistic regression different from a linear regression. Now in linear regression, we have this equation y equals a plus bx, where y is the predicted value and x is the feature. And we have b, which is the weight, and a is the constant term. Okay, this is linear regression, and the outcome or the output will be a continuous value. Now, taking the same equation forward, we have to now find out the probability of an event. Okay, we have to find out what is the probability of an event. So how can we use this same equation to find out the possibility that this event is likely to occur or not? Now, in statistics, you would have probably done this topic called as odds. Can anyone tell me what is the definition of odds? Was this topic covered?
The probability that event occur or not.
Event occurred or not. Okay. Okay, close. So odds is a ratio. Okay, it is a ratio of an event occurring divided by event not occurring. So P minus 1 by P. Or we can say P upon Q. Okay, so that is so odds is a ratio that defines the occurrence of an event. Okay, so defined as P by 1 by P, where P is the probability of that event occurring. So this, you have probably done this in the statistics chapter. Now I have to use the same concept of the odds to define what is my y variable going to be. So I'll be writing the same equation, y equals a plus bx from the linear regression. Now here my output is not going to be y, it is going to be p. Okay, so how do I get the probability that this event is likely to occur? So I'm going to convert the y into odds. Okay, so instead of writing y, so I will write this equation as p divided by 1 minus p equals a plus bx. Now I need to find out what is the value of p. So solve for p. This is just a little bit of mathematics. I won't get deep into this. So how do you get the value for p is by taking the log on both sides. So log of p by 1 minus p equals log of a plus bx. Okay, so this equation on the left hand side, this is known as the log of odds. So this is what you get as an output in the summary, that what is the log odds of a certain variable. Now, if I solve for p, the equation becomes p equals 1 upon 1 plus e raised to minus a plus bx. Okay, this is the final equation. So what is the probability of an event occurring? It is 1 upon 1 plus e raised to minus a plus bx, where a is the constant term, b is the slope, and x is the feature. And e, of course, that is the Euclidean, that is the power, minus 2.71. Okay, so this is the equation that gets formed in a logistic regression, and the value of p. Does probability have a range?
0 to 1.
It is always between 0 to 1. Okay, so this p value will always lie between 0 to 1. So if it is closer to 0, it means that the probability of an event occurring is very less. When the value is closer to 1, it means that the probability of the event occurring is on the higher side. Okay. So this function that gets generated here, p equals 1 upon 1 plus e raised to minus a plus bx. This is called as the sigmoid function. Okay. Sometimes it is also known as the logit function, L-O-G-I-T. So logit means it is the log odds of this function. So it is either known as a sigmoid function or a logit function. Okay, clear? Now, in a linear regression, how do you evaluate the model, or what do you draw? What happens? You get something called as a best fit line, isn't it? So you have this graph, X and Y graph. So you have the best fit line, and then you have the points around it. So the distance between the best fit line and the expected value, so that distance is known as the error. Now, in a logistic regression, since there are only going to be two classes, so we don't have any best fit line. Instead, we have something called as the best fit curve. Now, how does the best fit curve work? So we have the two probabilities, which can either be 0 or it can either be 1. Okay, so we have this box. Now, in between these two numbers, we have the midpoint. So let's assume it is the cutoff of 0.5. So what we are saying is anything which is inside this area of 0 to 0.5, I'm going to consider this to be as my negative class. Anything that is between 0.5 to 1, this I'm going to consider as the positive class. Okay, so now the line that gets formed, because I can have the points anywhere like this, okay, it can be scattered. So I want to cover as many points as possible. So I want to draw the curve something like this. So this becomes kind of an S-shaped graph. So S-shaped curve, also known as a sigmoid curve. Okay, so I can have the best fit curve, which is going to cover as many points as possible, such that I can have the maximum zeros predicted as zeros, and I have the maximum ones predicted as 1. So how do I ensure this happens? So I'll be selecting the best fit curve. So my curve, S curve can resemble like this, or it can resemble like this, or it can be something like this. Okay, so I can have as many number of best fit curve, just like we have as many number of best fit lines. So the best fit curve is the one which has the maximum accuracy. And this is measured using a method called as MLE, maximum likelihood estimation. This is 1 and this is 1. Any questions in the introduction part?
सर जो हमने लिनियर में जो लाइन फिट की थी, इसमें कर सकते क्या एक और में?
हाँ, मैं वो बोलता हूँ, I'll come to that point. Good question. यहाँ तक कोई any questions?
नहीं सर.
Okay. Now this is a typical interview question, that we have the equation y equals a plus bx of linear regression. Now, can I use this equation to fit a binary class? What do you think, based on whatever you have learned in linear regression and with the introduction of logistic regression? Why am I not using this equation to fit a binary classification? Can anyone guess why it is?
Sir, it doesn't cut the graph equally.
It doesn't cut the graph equally. Okay. Yes, you're right. Now, when you take the equation y equals a plus bx, okay, now a plus bx kya hai? A is the y-intercept, b is the slope, x is the feature. Now, if I take this equation, what is going to be my y value? Most probably, the y values will be greater than 1. Okay, it can be any number. It can either be less than 1, or it can be any range from infinity to infinity. Now, if I have to plot this particular output, now I know that my classification is always going to be between 0 and 1 because it is a probability. So 0, 1, this is 1, and this is 1. Okay, now if I plot a best fit line, so let us say this is my best fit line. Now, what is the problem here is that any value which is greater than 1. So how am I going to map these values? How do you set the threshold for all these numbers? I can also have values here. So how do you set the threshold for all these numbers? So this is going to be difficult because these are all continuous values. And it exceeds the limit, which is 1 here. So to avoid this problem, we are converting the equation from y into log odds. So that is why the y becomes p by 1 by p, and then the log of this. Now, what happens if I do this? I'm going to put all these numbers into a range between 0 and 1. So now I can say that any number which is less than, so if I take my cutoff to be 0.5, okay, since this is a middle point. So if I take this to be the cutoff, now there are chances that some of these values will be in this region and some of these values will be in this region. So now I can easily say that these numbers are belonging to a negative class, and anything which is greater than belong to the positive class. So that is the reason why we don't consider the linear regression equation in our binary classification or logistic regression, because it exceeds the limit of 1. Clear? Okay. Now we'll talk about the features now in the feature selection technique. Just like linear regression, the logistic regression also has some feature selection techniques. The most commonly used one is the summary of the data set. So once I summarize my model, so summary of the model, from this I can find out what are the significant features and which features can be eliminated. Second one. Now in statistics, you would have probably done that when I have a categorical data and I want to compare this with another categorical data to find out significance, which test will I perform? Which hypothesis testing will I do to find out whether this categorical data X and this categorical data Y, are they dependent on each other or are they independent? Yes, Ankita, Keshav, Mrinal.
Anova, sir?
Sorry?
Anova test? Anova?
No, it is not ANOVA. I have a categorical data and I have another categorical data, and I want to find out whether these two categorical columns, are they dependent on each other or are they independent? So that is done using a chi-square test. Okay, so I can perform a chi-square to find out whether my categorical feature has any relation with the Y variable. Just to give a small example. So let us say that I have an employee database. And the organization wants to find out the churning of employees. This is a very, very common example. An employee churn, you all know, the leaving of an employee from an organization and joining other organization. So churning is actually a big problem with companies. They want to retain as many employees as possible, but there are factors that cause an employee to resign and join another company or for whatever other reasons. So churning is actually an issue. So HR wants to minimize the churn, and they want to identify who is likely to leave the organization. What are the factors that cause churning in the company? So churning is a binary classifier. So it can either be 1, that means the employee is likely to leave, or the value is 0, the employee is likely to stay. So this is stay and this is leave. So leaving means it is churn. Okay, so we can see that this is a binary classification. Now, let us say that there are a list of features. For example, the features could be age, then it could be educational qualification, then it could be distance from the house, then it could be marital status, then it could be gender, for example. So there are lots of factors that the data set will have. Now I want to find if education, does it have any relevance in employee churn? Okay, now if you look at the education column, this is a categorical feature. Now, why it is a category? Because it can have only one value for an employee from a given set of n values. So, for example, education could be high school, or it could be graduation, or it could be post-graduation, or it could be doctorate, whatever it is, or postdoctorate. So you have a list of values. Now, does education have any role to play in predicting the churn? So this is a categorical column. This is a categorical column. Now, if I do a chi-square test on education and churn, so based on the output, I can decide whether this column education is dependent, churn is dependent on education, or are they independent? So if they are dependent, it means that this is significant. Otherwise, it is not significant. I can remove that column from my data set. Okay, so this is another way that I can do the feature selection on the data using the concept of chi-square on each of the independent features, which are categories. Then I have another technique, which is called information value. So this is once again a very useful technique, IV. So IV is again used only for the categorical data. And this is going to, it is simply a count of all the categories, and it is going to apply some log functions on it to find out the category of the importance of that particular category with respect to the Y variable. So I'll share that formula with you. This is, you have an inbuilt function to find out information value for a given category. So if I write information value on education with respect to churn, so this will return me a set of, it will return a number. So some number. And based on the range of the number, I can decide whether this particular number is significant or not significant. Okay, so that's all it is. So these are the three ways in which I can find the summary of the model. And from that, I can select the important features. Now in Python, we have another function which is called as feature selection for classification. So in case if you don't do any of these three techniques, there is another method called as feature selection for classification. And this method will take the training data, and it is going to give for every feature, it is going to give a score. So if you have 10 features, you will have 10 scores. So let me just write that down. So if you have, let's say, 10 features, so it is going to give a score for each of these features. So let's say X1 is 1.613, X2 is minus 0.439. This is 115.37, and like that, it will give you a score. So the way to evaluate this is, higher the score means more important, and conversely, less score or lower the score means less significant. So if I have to find out what are my top 5 features, so if I have 10 features, I want to find what are the top 5 features. So how do you find those top 5 features? You sort the data in the descending order and then take the top 5. So this will give you the top 5 features of the data set, of the training data set. And using those 5 features, I can do my second model. And from there, I can go on till I get the best accuracies. Okay, so this is how the logistic regression or a binary classifier works. So you have a sigmoid curve that is going to determine the best fit curve, because the range is between 0 and 1. It works on the principle of log odds, and it is the output of a logistic regression is the probability of the event. So based on the probability, I'll be converting my probability into a class by using something called as cutoff. Well, I'll explain the cutoff now. So any questions from anyone? Okay. Now we'll talk of this term called cutoff. So before that, let me also quickly cover what is the difference between linear regression and logistic regression. So what is the first difference? So what do you think are the differences between linear and logistic? So the first difference is in the equation. So one uses the y equals, the other uses the p equals, where y is a continuous value, p is the probability. Next, linear regression has assumptions with respect to data, with respect to errors. We have already done this in the class. What are the different assumptions and how do we validate those assumptions? Logistic regression does not have any assumptions the way linear regression has. So we do not have a lot of assumptions. Okay, but you still need to take care of a few things. That is the outliers and the distributions. So it is always good not to have outliers in your data. And it is also good if the numerical part of the data does not have a lot of skewness. But again, if you have extreme skewness, you try to convert it into a normal distribution. If that doesn't happen, then you just leave it as it is and you can fix it later on by using the cutoff. Okay. So we'll discuss the cutoff after we discuss the differences. Then the third difference. Now, if you look at the interpretation of the linear regression, we have y equals a plus bx. What is the meaning of this equation? This means that when x changes by 1 unit, what is the corresponding change in y? Okay, so change of x by 1 unit changes y by how much? That is how the interpretation of the linear regression is. Now for the logistic regression, we have P equals a plus bx. We just put a hat here. It is p hat and y hat. So p hat equals a plus bx. It means that change of x by 1 unit changes the log odds by how much? Okay, so if x changes by 1 unit, what is the corresponding change in the log odds of that particular record? So that is the interpretation of logistic regression. The next difference is, because the y variable is a number, so if I have a data called BMI, so the linear regression can predict, for example, a value for blood pressure. Whereas a logistic regression, if the data has BMI, it can predict whether a person is diabetic or not diabetic. Okay, so this is a number and this is a class. Clear? And yeah, there is one more. The error terms. In linear regression, we talk of the errors, which is sum of square errors. Whereas in logistic regression, we talk of the technique called maximum likelihood estimate. So max likelihood estimate. Okay, any questions from anyone in the differences?
Sir, for the 4th point, BMI is the number, let me say number and class. So it's like numeric values, right? For the 4th, we can say that it contains numeric values, LR, and logical consists of categorical values.
For the logistic regression or for linear?
For the linear, it has to be numeric values.
Yes, this is numeric.
Yes, and for the logistic, we can say that it is a categorical value because it has in or and like two options.
Yes, it is a category. I'll tell you how this works. The output is a categorical data. Okay.
Okay.
Now we'll see how this actually works.
Output means, in the sense, it will come in the form of 0 or 1, right?
No, it will not come in that way. That is what I'm going to explain it now. Now, if you look at the similarities of linear regression and logistic regression, both are similar in nature because both these equations, they give you a continuous value. Okay, y equals a plus bx and p equals 1 upon 1 plus e raised to minus x or a plus bx, they both give you a continuous value. So I can say that linear regression and logistic regression are similar to each other as far as the output is concerned. Now the difference is the y value has no range, whereas the p value has a range from 0 to 1. Is this clear?
Yes.
Now, if the p value has a range from 0 to 1, so how do I convert the p value into classes? Because my output for a logistic regression is, it can either be 0 or it can be 1. Okay, it has to be an integer which is 0 or 1. So this is where we have something called as a cutoff. So a cutoff value is going to tell that any probability that lies within a given range. Okay, for example, if I'm getting the p hat prediction and this number comes to be, let's say, 0.31764, okay, something like this. It's a float number, so I'm putting the numbers like this. And if I'm getting for the next record, the prediction as p hat equals 0. Let's say 63781. Now, how do I convert these values into a class 0 or 1? Because end of the day, I want this particular record to show me whether it is 0 or whether it is 1. Second record to be 0 or 1. So I can define something called as a cutoff. Now, if you remember in the first or second slide, I showed you that we have this range of 0 to 1. Now, 0.31 is going to lie somewhere here. Okay, assuming that this is the cutoff of 0.5. So 0.31 will lie somewhere here. 0.63 will lie somewhere here, let's say. So I can say that anything which is less than any probability which is less than 0.5, I can classify this as 0. So even if I get a probability value of 0.01, which is going to be somewhere here, even this will be considered as class 0. And anything which is greater than 0.5, I want to consider this to be as class 1. So this is how you convert the probabilities into classes. So the output of a logistic regression, if you print the predictions, you will see that the predicted y will be a list of probabilities. That is, what is the probability of the event? So for record 1, you will have some probability. For record 2, you will have some probability. So how do you convert the probability into a class? Is by using this cutoff value. So I can define my own cutoff. By default, it is going to be 0.5. You can use this as the starting point. And according to the number of correct predictions and false predictions, you can change the cutoff from 0.5. You can bring it down to 0.3, or you can take it up to 0.7. So that is up to you where you set the cutoff. So this is how the conversion of predictions into the class happens. Is this clear to everyone?
Sir, that value does not depend on the domain, right? When we consider 0.5, it does not depends on the domain, right?
No, it does not depend on the domain. It depends upon the accuracy of your results. Okay, I'll come to that accuracy in some time, that how do you evaluate a given model? How good or bad this model is. So we'll talk of the evaluation, then you will understand that how the cutoff can be changed.
Okay, got it.
Any questions from anyone? Okay, so let's go to the next section. Is this going too fast or too slow? Please let me know. Is the pace okay with everyone?
Yes, sir.
Okay. Now we spoke about the features in the beginning of this lecture. I told you that there were two sets of features, the numeric features and the categorical feature. Now, when you have a numeric feature, then there is no problem. But when you have a categorical feature, then I have to do a special treatment on this categorical feature so that I can build my model. Otherwise, the model cannot be built. Okay. Now, what is that special treatment? Now, let's take a very simple example of a column called gender. Now, usually the value of gender will have the text like this, male and female. Okay. Now, let's say that I have 100 records and there are 45 male records, customers or employees, and then 55. So total 100 records. And my output is, let's say, employee churn, which is category. Now here I have a gender column which contains the text male and female. And here I have a churn that contains the value 0 and 1. So whenever I have these texts in a categorical column, I cannot use the values as it is. So these texts have to be converted into numbers. And this process of converting text to numbers is called as dummy variables. Have you done this in the class, the concept of dummy variables? Yes, no? Okay. So can you tell me why do we need to convert the text into numbers? Why can't I use this gender as it is? Why should I do this conversion? plotting the graph. Sorry, what is the meaning that plotting the graph?
Sir, you need the number data to plot the graph, gender against churn, for example. Categorical variable, we cannot plot a graph with the text.
See, for plotting the graph, as long as it is a two-dimensional graph, it is okay. But if I have 10 or 15 features, then even plotting a graph is going to be impossible. I can do a count plot. Even if I have the text, I can do a count plot and plot it. That is not an issue, but that is not the reason. See, go back to the equation. The equation is P hat equals A plus BX. Okay. Now, assume that I have only one feature called gender. So what is this equation going to be? It is going to be A plus B into gender. Now, what is the value of gender? If I take the first record, this is record number 1. So let's say the gender is male and the output is 0. And the second record, the gender is female and the output is 1. Okay, so what is going to be my data, my equation? It is going to be P hat equals A plus, so let's put some dummy values. So A is going to be, let's say, 0.113 plus, let's say 0.027 multiplied by, so this is for the first record. So this is P hat of 1. So what is the value of gender? It is male. Okay, now does this equation make any sense? What will be the result of this? Yes, anyone? If I do a multiplication, what will be the result of this? First of all, can you multiply this? This will be an error because I'm multiplying a number with a string. Okay, so you cannot do this. In maths, you can only multiply numbers with numbers. Okay, so it has to be a number. It can either be 0 or 1 or whatever may be the number. So this X, it has to be a numeric column. Okay, so it cannot take a string like this. So that is the reason we want to convert every value that we have in a categorical column into a numeric form. So now if you change this gender, and instead of male, if I have 0, and for female, if I have 1. Now see what happens to the equation. So probability of 1 now becomes 0.713 plus 0.027 multiplied by 0, which is fine. And P2 equals 0.713 plus 0.027 multiplied by 1, which is also fine. Okay, so now based on the probabilities, I can set my cutoff and then predict whether P1 is going to have 0 or 1 based on the cutoff, and whether P2 is going to have a 0 or 1 class based on the cutoff. Is this clear to everyone?
Yes, sir.
So how do you create these dummy values, these dummy variables? So we'll quickly discuss this and we'll take a break. So the topic is dummy variables. Now, whenever you have a categorical data in Python, you need to convert it into a dummy variable and then have it in your data set. Otherwise, during model building, you will get an error. So the formula for converting a dummy variable is a dummy variable equals number of values of the categorical data minus 1. Okay, and the one value which is left out, so the value which is left out, that is called as a reference class. Now, so let's take an example. So let's say that I have a categorical data called let's say dwelling type. Okay, let's take a ticket. Ticket. So let us say that you have some ticket. Now the ticket types can have 3 categories. I have a first class ticket. I have a second class ticket. And then I have a third class ticket. Okay, so this is clearly a categorical data. Now, according to the definition, dummy values equals number of values in the categorical column minus 1. So I can take any 2 to be the dummy values. Okay, so it can be any 2 or any n minus 1. So let us take the dummy values to be first class and second class. So if first class and second class are the dummy values, what is the reference class? Reference class will be the third class. If I take second class and third class to be the dummy values, my reference class is going to be the first class. Or if I take the first class and third class to be the dummy values, my reference class is going to be the second class. Is this concept clear?
So repeat again.
So let's say that I have a column in my table called ticket type. Have you heard of this data set called Titanic?
No, sir.
Okay, have you heard this term Titanic? The ship that sank.
Yes.
Okay. Now, when the machine learning was becoming, when it was developing, and when these algorithms were getting formed and the predictions were getting, it was gaining popularity. So one of the famous data sets that people were using was called as the Titanic dataset. So Titanic, as you all know, is the ship that sank in the Atlantic. And they had a group of columns and they wanted to predict which passenger survived and which passenger did not survive based on the list of features. So one of the features that was there was what was the type of ticket. So we had a ticket type, and the Y variable that was there was called survived. So 1 means the passenger survived and 0 means the passenger did not survive. And in those days, there were 3 different types of tiers. So we had a first class, which was the ticket type was first class. Then there was a second class ticket, and then there was a third class compartment, or not compartment, third class ticket. Okay, so first class, second class, and third class were the feature for this column called ticket. So ticket type. So this is a category. This is a category. Now, when I have 2 categorical columns, and if I have to convert my feature into a number, I am going to use this concept called dummy variables. The formula for dummy variables is the number of features, number of values in the feature minus 1. So here ticket type is the feature. Number of values are FST, first class, second class, third class. So N value is 3. So dummy value is going to be N minus 1, which is going to be 3 minus 1, which is equals 2. So that means out of these 3 values, any 2 can be the dummy variables. So if I take first class and second class to be the dummy values, the one which is missed out, which is the third class, that is called as reference class. If I take the values for dummies as second class and third class, it means that first class becomes the reference class. And if I take first and third to be the dummy values, S becomes the reference class. Is this clear to everyone?
Yes, sir.
Now, why should we take only N minus 1 and why not we take the entire set of values? So let me quickly explain that. Okay, there you go. Now, let us consider the same example, and I'm going to draw this matrix. So I'm going to put the first class, second class, and third class, and I'm going to put first class, second class, and third class. I'm going to put it like this. Now, if someone has a first class ticket, so that means he cannot be in the second or third. So I'll put a 1 here. I'll put a 0. I'll put a 0. Someone who has a second class ticket, that means this value is going to be 1. This is 0 and this is 0. And someone with a third class ticket, this is going to be 1. This is going to be 0. This is going to be 0. Okay, this is how you define the matrix, which is also known as a one-hot encoding method. Okay, now here we have a 3 by 3 matrix because I have 3 values, but formula is n-1. So I can do the same thing using a 2 by 2 matrix also. So how do I convert this into a 2 by 2 matrix? Is simply by removing one of these rows and columns. So if I remove the T, that is if I consider my dummy values to be first class and second class, so this is first class and this is second class. So someone who's in the first class will be 1, second will be 0. Someone who's in the second class, this is going to be 1, this is going to be 0. Now, what about the third class? Someone who has a third class ticket, how will you represent that information? This is going to be 0, this is going to be 0. So I don't need the last row and last column. Using just these two information, I can also represent my third class. So that is the reason why the formula is n-1 for the list of dummies, and the one which is missing is called as the reference class. Is this clear to everyone?
So this is accuracy and prediction chart, na?
No, this is the one-hot encoder. How to represent a categorical data in zeros and ones. Why we need n-1 for our dummies? So this is a n by n matrix, and this is an n by n matrix. Okay, so this is how the representation of the dummies. Now, how does it translate into a data set? So let me take a simple example of the same data of Titanic. So let's take age. Let's take ticket type. And this is ticket type. And here it is going to be survived. And this is record number. So let us say I have 3 records, record 1, record 2, and record 3. Age is 42, 29, and 13. Ticket type first, third, second, and survived, I will say yes, no, yes. Okay, this is the original data set. Now, after I apply the dummy variables or the one-hot encoding method, how does my data transform itself? So the record number will remain as it is. The age will remain as it is. Now the ticket type will change. If I take first class and second class to be my dummies, so I'll have ticket type, first class, ticket type, second class, and then the Y variable, which is survived. Now let us look at the first record. Record number 1, age is 42. Now, what is the ticket type? It is first class. So first class will have the value 1. This will be 0. and survived will be yes. Instead of putting yes, I'll put 1. Because Y means 1, N means 0. Second record, the age is 29. What is the ticket type? It is third class. So this is going to be 0. This is going to be 0. And this is going to be 0. What is the third record? Age is 13. Ticket type is second class. So that means this is 0. This is 1. And this is 1. Is this clear to everyone?
So third class is a reference now, no?
Third class is a reference class. So 00 means customer number 2 or this passenger has a third class ticket, which is what I have here. I'll tell you what is the importance of the third class, the reference class. But have you understood this one-hot encoding technique? What happens when you convert the data into one-hot encoding? This is the original data, and this is what happens after the conversion. So you get the data set in this form. So that is why this is called as a dummy variable, because the variable that I have here, TTF and TTS, ticket type first, ticket type second, this is not actually a variable. It is a dummy variable. It acts like a dummy variable. Clear? Any questions? Okay, so we'll take a break, and after that we'll discuss 2 more points. That is the importance of the reference class. That is, how do you interpret the reference class? Why do we need the reference class? We'll take one example. And the second one is evaluation technique or evaluation metrics of a binary classification. So these 2 we will do, and then followed by, at least we can start the hands-on. Okay, so 10:30 we'll meet in about 15 minutes. Okay, let's continue. So before the break, we saw the concept of a dummy variable. So now we'll understand how is dummy variable interpreted and what is the use of the reference class. Now, in the example of the Titanic, I told you that there was a ticket type and there was a survived column. Now, if you remember in the linear regression, we did a summary of the model. And the summary gives you a lot of numbers. Okay, so you get the numbers for the features and you also get the p statistic and the p value. Okay, similarly in the logistic regression also you get a summary where you get the values for each of the features. Now for the ticket type, I'm going to take the second class and the third class to be the dummy variables. And the first class becomes the reference class. Now, if this is the case, now if I do a summary, now let's assume that the value that I get in the summary for the second class. Okay, so the summary I get ticket type underscore second class. Okay, now this gives me a value, let us say minus 1.27. And I get the summary for the third class, which is ticket type underscore T, which is the third class. And this value comes to be minus 2.24. Okay, I'm just taking some numbers. Now, how do you interpret these two numbers? What is the meaning of these numbers? And why am I not able to see the value for the first class? Now, the interpretation is is this clear to everyone? The example here? Hello? Hello? Okay. So now the ticket type second class, the value is minus 1.27 and the ticket type third class is minus 2.24. So the summary output that you get here, these are nothing but the log ons. So the summary of a logistic regression, it gives you the log ons. Now the interpretation is going to be, what is this meaning of this number minus 1.27? So what we do is we convert the log ons into ons. And after that, we do the interpretation. So now what is the odds of this number minus 1.27? So how do you convert log odds to odds? So we do the exponent. So exponent of minus 1.27. Okay, so this will give me the value for the odds. So let us say Okay, let me just calculate and see. Exponent of minus 1.27. So this gives me a number 0.208. Okay, so this value that I get is known as the odds. Is this clear to everyone? Now, similarly, if I take the exponent of the number minus 2.24, I get an odds value. So let me calculate it, and this comes to my 0.1063. So this is again an odds. Okay, you can use the calculator and find out that if I take minus 1.27 exponent, you will get the odds value, which is 0.208 and 0.106. Now, what is the meaning of these two numbers? So this is where the reference class comes into picture. Now, what is the value of the reference class? It is the first class ticket. So the interpretation is going to be with reference to a passenger having a first class ticket. So with reference to the first class ticket, the odds of passenger surviving. Okay, the odds of passenger surviving having a second class ticket is how much? 0.208. So that means between a first class ticket and the second class ticket, who has a greater chance of survival? It is obviously the first class passenger, because the second class passenger, the odds are only 0.208. So this is how the reference class interpretation is done with respect to its dummy variables. Is this interpretation clear to everyone? Hello? Mrinal, Tejas and Yash, appreciate if you could say something. Okay. Fine. So similarly, if I'm looking at this value of 0.1063, I can say that, so the interpretation is for this, or for this one, I can say with respect to the first class, the odds of passenger surviving having a third class ticket is how much? 0.1063. So that means between a first class passenger and the third class passenger, who is more likely to survive? It is again going to be the first class passenger. So if you look at the Titanic data set also, you will find that if you are given a data set of first class, second class, and third class tickets, the maximum survivors will be in the first class, followed by the second class, and then you have the third class. Any questions on the dummy variables? Okay, so now we'll go to the evaluation. I'm assuming that you have understood everything. So now we'll go to the evaluation metrics. Now, if you remember in statistics class, you would have probably done the Naive Bayes. Okay, so posterior probability. So we're just going to touch upon a few points from there and come to the evaluation technique. Now, let's take an example of how the binary classification evaluation works. So there are two main things in this. Number one, we have something called as a confusion matrix. Then we have a list of measures. So in this measure, we have the first measure as accuracy. Then we have precision. And then we have recall. And if you want to go further, we also have something called as a F1 score. Then the third measure that we use, that is called as the area under the curve and the ROC. So ROC curve and the area under the curve. So these are the three main evaluation techniques that we have for a binary classifier. So what is the confusion matrix going to give us? Now let us consider that, so we have, let's say, a patient. Okay, let's say we have a person. Now this person is going to test for, let us say diabetes. And he gives the blood, he does a blood test. Now, what are the chances that, what are the different possibilities that you can have? So this guy is a healthy patient, a healthy person. So I'll put a plus here. And this person is actually a diabetic person. So diabetic person, so that means a negative. Now, when the healthy person is tested for diabetes. So what are the different things or the different combinations that I can get when this person tests for diabetes? Okay, so let us write down all those combinations. So healthy person can be tested as healthy, or the healthy person can be tested as not healthy. I'll put not healthy. Now this is the non-healthy person. So if this person tests, this will return two things. Not healthy will return as not healthy, and not healthy will return as healthy. Is this clear to everyone?
So repeat again this.
So here we have two people. The one at the top, this is the healthy person. And the one at the bottom, this is the not healthy person. Okay, this is healthy and not healthy. Now this healthy person, when he does some kind of a test, so you can have two possibilities out of the test. Let us say you're doing a blood test. And you're testing for, let's say, diabetes. So the healthy person who does not have any diseases, when you do the blood test will say you are healthy, or the blood test will say you are not healthy. So you can have two outcomes. Then we come to the second patient who is actually a diabetic person. When this guy does a blood test, the blood test can have two outcomes. The non-healthy person can be classified as non-healthy, or the unhealthy person can be classified as a healthy person. So you can have these four outcomes. Clear?
Yes, sir. Yes.
So out of these four combinations, which are the correct predictions? Which are the false predictions? Healthy as healthy is correct prediction. A non-healthy person predicted as non-healthy, this is correct predictions. Someone who is healthy is predicted as not healthy. This is a wrong prediction. A person who's not healthy predicted as healthy. These are wrong predictions. Clear?
Yes, sir.
So the confusion matrix is going to tell how many were the actual data, and in the predictions, how many are positive, how many are negative. So this is a 2 by 2 matrix. Okay, so let's take an example. So let us say that we have 100 patients. Okay, so let us write this. So this is the actual data, and this is the predicted data. So this is actual positive, actual negative, predicted positive, predicted negative. Now in the actual positive, let us say this is 25. And how many healthy people are there? This is 75. Okay. So here in my actual data, how many positive classes are there? 75 positive classes. Sorry, 25 positive classes because I'm predicting diabetes. So that becomes my positive class. And how many negative classes? The healthy ones, that is 75. So here actual negative is 75. And total number of people is 100. Now, out of these 100 people, 75 people are healthy people. That means they are the negative class. So this is healthy. And these are diabetic. Okay, now the test comes and we get the report. So out of this 25 people who are diabetic patients, so I can have the result as diabetic predicted as diabetic. So let us say this number comes to around 18. So if 25 people are there who are diabetic, out of which 18 people have been predicted correctly as diabetic, it should come here. So the remaining 7 people are predicted as healthy people. So this number will become 7. Is this clear to everyone? Okay. Now, out of the 75 people who are healthy, if 65 people have been correctly predicted as healthy, that means the remaining 10 people out of 75, which is this number, they are predicted as diabetic. Okay. So now if you look at the count, my model has predicted how many people as diabetic. 18 plus 10, which is 28. And my model has predicted how many people as healthy. 65 plus 7, which is 72. And the total comes to 100. Okay. So total positives predicted is 28. Total negatives predicted is 72. Okay. Total predictions. So it doesn't mean that they are the accurate predictions. They are the total predictions. Is this clear to everyone? So now let us go to the terms and we'll see what are the different methods that we have. So let me draw this matrix again. So we have this is positive class, this is negative class, this is positive class, this is negative class, this is 25, and this is 75. Now out of which this is 18 and this is 7 and this is 60. How much was the 65? And this is 10. So this is 28 and this is 72. And this number becomes 100. Okay, so this is the actual data. And this is the predicted data. So actual data is along the rows and predicted data is along the columns. Now, which numbers represent the correct predictions? (18) and 65. Okay, so these are the correct predictions. So this is called as true positive, and this is called true negative. Okay. Now let us look at the other two numbers, 7 and 10. What is 7? Out of 25, they have been predicted as negative. So that means this is a false negative. Okay. Whereas the 10, it is the predicted part. So this is predicted as a positive. So this is known as false positive. Is this clear to everyone? So now I can find out what are the other measures. So the measures are accuracy. So accuracy is what is the total positives predicted by my model? What are the total negatives predicted correctly by the model? So total positive plus total negative divided by total number of observations. So here I can say it is 65 plus 18. So that is going to be 83 upon 100. So which is 0.83, or I can say 83%. So 83%. Okay, so accuracy takes care of all the correct predictions in my model. That includes positive class predicted as positive, negative class predicted as negative. Then I have another measure called as precision. So precision means what are the total number of positives predicted in my total positives predicted by the model. So total positives predicted. So that is going to be given as total true positives divided by true positives plus false positives. So this is how much? 18 upon 28. So if I do this calculation, I'll get 18 divided by 28, which is 0.642. 0.642. or it can be written as 64.2%. Okay, so precision means what are the total positives predicted by my system. Then I have the next measure, which is called recall, also known as sensitivity. This measure is going to find out what are the relevant positives. Okay, so one is all the positives, one is the relevant positives. So relevant positive means out of the positives, how many are actually positives? So that means true positive divided by true positive plus false negative. So which is how much? 18 upon 25. Now, if I do the calculation, I'll get 18 divided by 25 is 72%. So this is 0.72, which is 72%. Then I have the last measure. I have two more measures. One is, so the fourth one is called specificity. Specificity means how many negatives have been predicted as negatives. Just like we have the relevant positives, specificity means what are the relevant negatives. And that is given by true negative divided by true negative plus false positives. So how much is that? True negative by false positive, true negative is 65 divided by 75. Now, if you do this calculation, I get 65 divided by 75, which is 0.86. 0.87, or I can say 87%. And then we have the last measure, which is known as the F1 score. So which is a harmonic mean of precision and recall. Okay, so the harmonic mean formula is 2 times PR upon P plus R. So if you do the addition, if you do this calculation, you get the F1 score of this model. So which is a combination of precision and recall. So you can just do this calculation and find out. So 2 times (0.642) into divided by so that comes to around 0.68. So this is approximately 0.68, that is 68%. Okay, so these are the measures that we use to evaluate how good my model is. So if I have to evaluate this particular model based on these numbers, do you think my model is good or not good? So accuracy is how much? 83%. Recall is how much? Okay, Yash says a good model, so let's find out. So accuracy is 83%, recall is how much? 72%. So this is the recall for the positive class. And what is the recall for the negative class? It is 87%. So based on these numbers, I can say this model can be considered as a good model. Now, why it is a good model? Because overall accuracy is high. The positives predicted as positives is also high. And the negatives predicted as negatives is also high. So I can say this is a good model. Okay, clear?
Yes, sir. So this value can be in linear regression, use can be mean square error. Can be replaced by accuracy prediction.
No, this cannot be used in any way for a linear regression.
No, sir. This is similar way na use. जब हम linear में mean square निकालते हैं, root square निकालते हैं, r square निकालते हैं, logistic में यहीं पे accuracy prediction और recall निकालते हैं ना हम.
हाँ, ये evaluation matrix है. This is the confusion matrix.
Okay.
और ये जो भी measures है, these are the classification reports. Precision, recall, all these are classification reports. Confusion matrix will tell you overall what is the performance. So how do you evaluate? Based on all these measures. Okay, now apart from this, there is one more measure that is frequently used. And that is called as the area under the curve and receptive operative characteristic. So ये जो this particular curve graph, what it does, it is going to plot two values. One is what is the true positive rate along the y-axis and what is the false positive rate along the x-axis. And it is going to do this against a dummy model. So if let's assume that I have a dummy model. So dummy model is something which is 50% accurate. Okay, so let's assume that this is a 50% model. I would say 50% accurate model. So as compared to a 50% accurate model, how good is my model? That is what is going to be done by the ROC and the AUC. So how many positives are predicted? And what is this is actually 1 minus FPR, not FPR. It is 1 minus FPR. So true positive and 1 minus FPR. So if I'm able to get a graph, something like this. So that means this distance between the dummy model or a 50% accurate model versus the other model, this distance should be maximum. And if I get a maximum distance here, it means I have a good model. So that means my model is very accurate. Okay, so let's assume that I have this particular model that goes like this. So if you look at this distance, this is the maximum. If I take another model, which is going to be something like this, let's say like this. So between this distance and the blue distance is maximum. So that means the blue distance is giving me a much higher accuracy compared to the violet distance. So the blue model is better. And what is the area under the curve? So area under the curve is this entire region from the blue from here to here. Let me just mark it. So this entire region is the area under the curve. So that number should be as high as possible. So if this is the blue region, this is the area under the curve. And if this is the violet region, so let's mark that also. So here we can see that the violet region is having a less area compared to the blue region. So that means this is not that accurate, whereas this is highly accurate. So this is known as the area under the curve, and the graph is known as the ROC curve. Is this theory part clear to everyone? Okay. Okay, so that wraps up the theory of logistic regression. So any questions from anyone before we start the hands-on? Have you all completed the linear regression project assignment that I gave you yesterday? Hello? Do you want to do it now? Because there are only 2-3 people in this class today. So do you want to start with the logistic regression hands-on, or do you want to first finish the linear regression? Okay. Okay, fine. So do you think you can finish the linear regression by 1 o'clock today? If I give you time till about 12:45, 1, can you finish it by then? Okay. Okay, fine. So please finish the linear regression, what we discussed yesterday. And we will have a quick discussion after that if you want, in case if you're having any trouble. And after that, we will start with the logistic regression hands-on. Okay, so please finish linear. Okay, I'll wait. I'll be here in case if you have any questions, you can ping me.